Good morning. I am Shanti, working as Assistant Professor in Sri Ishwar College of Engineering in the CSE department. Now we are going to discuss about simple code generator algorithm in the compiler design subject. A code generator. You already know what is code generator. It is the last phase of the compiler. It will accept intermediate code generated output, that is 3 address code, as the input to the code generator. It will produce the target code, that is the assembly level language. So it generates the target code for a sequence of 3 address statements using next use informations. What is next use information? For example, if you consider you are having the statement y equal to x plus z. Here, y may be a live variable or dead variable. In this statement in y equal to x plus z, suppose y, the result of y is going to be used in further intermediate statement means you can say y is the live variable. Suppose if it is not used in further evaluation, then that is called a dead variable. So if it is a live variable, you have to use further the remaining statements in the 3 address statement. That is called the next use information. Code generator uses the function called the getRegister to assign registers to variables because 3 address code contains only operands and operators. We have to assign the memory locations for each and every variables in a 3 address statement. So here we have to consider register as the storage device. So we have to allocate for each and every variable, allocate registers to the each and every variable. Then we have to evaluate the result. That is y is equal to x plus z. X plus x and z is added. The result will be stored in the variable y. The y contains the computed result. That is also kept in the register as long as possible, which means result is neither in another computation or end of procedure call or end of block. Suppose the result of the variable will be used in further in your process of the program means that should be stored in a particular place. That is called the registers. That should remain in a register. Then only you can able to use that variable in a further calculation. Next, end of the procedure call, you have to store all the variables in a particular register. Similarly, end of the block also, you have to store all the variables in a register. So, register is needed to store all the variables in a program. And also, it checks whether the required 3 address statement is stored in a available registers. Code generator algorithm is implemented by descriptors. So we have two types of descriptors. One is register descriptors, another one is address descriptors. What is register descriptor? It keeps track of what is currently stored in a register at a particular point in the code. That is, if you are having the local variables or any arguments, global variables, all these things are updated in the register. That is, for example, move a comma or not. Here a is a variable that is stored into the register or not. Suppose here you are that is you are moving the value of a into the register or not. Here or not contains the a. Next you are having the address descriptor. It keeps track of the location where the current value of the name can be found at runtime. For example, register descriptors are registers, stack allocation, memory addresses. Suppose if you want to update the address descriptor, you have to move the value into the registers. See here, move a comma r naught. The value of a is moved into the register r naught. Then you are moving the r naught into the register r1. Here, the value of a is stored in both register r naught and r1 because so here's so you can say you can update the address descriptor A is in R0 and also in R1. Suppose A is a reused variable, that is the result of the A will be used in the text use means that will be stored in the two registers R0 and R1. You can access from the R0. That is the R0 is the register that contains the value of A. This will not be removed. Uh, this will not be removed. So register descriptor stores the value in a register. Address descriptor track the location where the current value of the name can be found at runtime. Suppose this particular variable is stored in the more than one location, you have to find out the opt location by using the address descriptor. Here A is stored in the two locations R0 and R1. If you want to the location of the A, you can access from R0 or R1, not in both. That should be updated by your address descriptor. Code generator algorithm. Here, the input to the code generator is the intermediate representation, that is 3 address format. X is equal to Y operator Z. First, set the location. You are having the get register function that is used to find the location of the result, computed result. Here get register function contains two arguments, that is the value of Y and Z. Then that function is called here get register of item IZ. Here Y is stored in a register R, that R only holds the value of Y. That is Y has no next use. It is a dead variable. Then you have to update the address descriptor. Value of Y is no longer in R. This value will not be used in the further computation. Or else return a new empty register if available. Suppose Y is not in a register R, then you are having the more number of registers, empty registers, then you have to allocate that. Else, if X has a next use in the block, find the occupied register R. That is, X is a live variable here. So you have to move that variable into the more than one location. That is, here more register is moved into the memory location. Then return a memory location. And also it return a register. That is, the value of X is stored in both the register and memory. So it will return the register and also memory location. Both contains the variable X. The second, here you are checking whether Y have the particular location. Y is not belongs to the only one location means then you have to move Y dash comma L. Here Y dash denotes one of the locations where the value of Y is available. That is Y may be in register or in memory. When you are taking the Y value from the memory, it takes more task because memory have the task for processing the codes. So register have more tasks. So better you choose the registers. So here Y dash contains the only one location of the value, only one location of the X, that is L. Next operator Z comma L, where Z is one of the location of the Z. Suppose Z is stored more than in one location, that is register and also in memory, you have to select the register because register task is register have no task. So next you have to update the register or address descriptor of X to include the location L. Now you have to find out either L is a register or memory. If it is a register, you have to update it register descriptor. Let's see if Y and or Z have non-next use and is stored in a register, update the register descriptor to move Y and Z. That is, this has these two variables is or dead variables means it will not going to be used in further computation. So you have to update the descriptors and this value of the Y and Z no longer will be used. You see the statement, you got the statement X is equal to Y. Here Y is assigned to the variable X. Here Y is in register or memory. But suppose if Y is in register, then change the register and address descriptor to record that X is found only in register for Y. Suppose if y is in memory, you have to invoke the getRegister function and load the y value and make the location of x. That is here the x value is in memory. Here the x value is found in the register. Here we will see some examples for the code generation. Here you are having the set of intermediate three address statements. That is t equal to a minus b, u equal to a minus c, v equal to t plus u, d equal to b plus u. For these statements, you have to generate the target code. See here, t equal to a minus b. Here a and b are variables. You have to move A into the register R0. Then you have to subtract the B from the register R0. Then parallelly you have to update the descriptors, register and address descriptor. If register is empty initially, then you have to allocate the result, computed result key into the register. So here a generated code R0 contains the results of the A minus B, that is T. So you have to update, R0 contains T. In address descriptor, T is in R0. Next we are having the statement U is equal to A minus C. Here A is moved into the register R1, then this value C is subtracted from A. The result is stored into the register R1. So here you update the descriptors. R0 contains T, here R1 contains the U, and also update T in U R0, U is in R1. Next, similarly, V equal to T plus U. Here T is in R0, U is in R1. So you can add R1 and R0. So the result will be stored into the register R0. So R0 contains the V, then R1 contains the U. Then you update the address descriptor. Next, we are having D equal to V plus U. Here, add R1 and R0 because R1 contains the U, R0 contains the V. The result will be stored into the register R0. Then the final result will be stored into the variable D. So you have to move register R0 into the variable D. Here R0 contains the D. So final result, the computer result are updated in both R0 and memory, more than one locations. See here another example how to generate the target code for the indexed assignments. Here A is equal to B of I. B of I is an array variable that is assigned to the variable A. So here I is the location. Location may be any value. Here suppose I is in register Ri, you have to move the register uh, array of register into the register R. If I is in memory Mi, then you have to move Mi into the register. That is move of B of R comma R. Suppose I is in stat, then you have to move stat into the register, then move the content of the register in an array is into the normal register. Here the value 2, 4 and 4 are uh, is known as the cast of the instructions. Here, move of B comma Ri comma R. Here, cast is 2. That is, move the instruction that contains the task 1. B of Ri is the register that contains the task 1. So, you have to add 1 plus 1. That is, you are having the 2. Next, I is in memory Mi. Here, you are having the two instructions, move Mi comma R, move BF for comma R. Here instruction move have the task 1. So for this move 1, again you are having one more move instruction 1. So you can add 1 plus 1, 2. Then you are having the memory 1, 3 plus array plus 1. 3 plus 1 is equal to 4. That is, whenever you are calculating the instruction chart, instruction have the task 1, normal variables have the task 1, then memory have the task 1, array and pointer variables are have the task 1, but registers do not have any task. So they are all free. Next you can take this. Here you are having two instructions. So task is 2, then start task is 1, 2 plus 1, 3. Then B of R, it is an array of register. Cast is 1. So totally 4. Here the B of I is assigned to the variable A. See here A is be a live variable. You can use this A into the further computation. Your next assignment is B, that is assigned to the array A of I. Here also I is in register or memory or stack. So you have to assign the value of B into the array variable A of I. So you have to move B into the A of Ri. Here suppose I is in memory, first you have to move that value into the register. So move Mi comma R, then you have to move the value of B into the array of register A of R. Suppose I is in stack, again you have to move that stack value into the register, then you have to move B into the A of register. Here, 355 are called cast, instruction cast. For this instruction, move is an instruction, so it have the task 1. B is a variable, they have the task 1. A of array is an array, so it have the task 1. So you have to add 1 plus 1 plus 1, that is equal to 3. You take these two statements. Here you are having two move instructions, so task is 2. One is memory, 2 plus 1, 3. Then you are having one variable, 3 plus 1, 4. Then you are having the array. Task is 1, 4 plus 1, 5. Total task is 5. Next, here you are having the two instructions. So task is 2. For array, task is 1, 2 plus 1, 3. Then variable 1, 3 plus 1, 4. Array 1, 4 plus 1, 5. So total task is 5. Next, similarly, you calculate the pointer assignments. Here, pointer is assigned to the normal variable A. Pointer is maybe in register or in memory or stack. If it is in register, directly you can move the value of that pointer into the variable A. Suppose in memory, first you have to move into the register, then you have to move the pointer to the register into the register. If it is in stack, you have to move that stack value into the register and pointer to the register is moved into the register. Similarly, for each instruction task is calculated here. For example, move is an instruction, it will take task 1, pointer takes task 1. So normal variables also take task 1. So you can add, this is star RP is a pointer to the register. So register does not contains any task. So move task is 1, task for A is 1, so it 1 plus 1, 2. Next, two move instructions have the task 2. Here memory pointed to the memory. So this task is 1. So you can add 2 plus 1, 3. Let's see, here you are having two instruction 2. Stack pointer is 1. So 2 plus 2 plus 1. Total task is 3. Next, conditional statements. This can be implemented by two ways. The first way is value of the register needs the retrieval. You are checking the two values. X is less than y. Then that value is, that may be a negative value or 0 or positive or non-negative, non-zero or non-positive. If any one of the value is there, then you have to branch the instruction. If X is less than y, then go to Z. It is implemented by subtracting X from Y, then find the Y from X in a register R and then jump into Z if the value in the register R is negative. The another way of implementation of conditional statement is using condition codes. Instead of doing all these process, you can have the instructions, that is compare C, M, P, X and Y. After comparing this, by default it will take calculate the subtraction of X and Y and find out where this value have to jump. Next, we are having the C Z less than or equal to jump Z. This instruction tells jump to Z if the condition code is negative or 0. Next, we are having another type of condition codes. Your statements are X is equal to Y plus Z. If X is less than or equal to less than 0, then go to Z. You have to convert target code for these two statements. First, you are converting X is equal to Y plus Z. Here, move Y into the R0, add Z to the R0. So result will be stored in the R0. then you have to move R0 into the variable X. Next, we are having the if X less than 0, go to Z. That is, we are having the uh, instruction Cj less than. It will jump to Z if the condition code is negative. So the single instruction will evaluate this full process. That is, if it's less than 0, go to Z. This will be automatically done by the Cj less than Z. So till now we have discussed about the code generator algorithm. Here you have to mainly know about what is the output of code generator, what is your input to the code generator, then code generation algorithm. Mainly this algorithm deals with the two descriptors, address descriptor and a register descriptors. You have to know that what is address descriptor and register descriptor. Next we are having the examples, how to generate the three target code for the given three address statements. Parallelly, you have to update the register descriptor and also address descriptor. Register descriptor contains only the computed results of the three address statement. Address descriptor, you have to access the address of the value in a memory, that may be in a register or memory. So these are all the another the example. Finally, you are having a conditional statement. You should know here that what is the condition codes, that is Cz less than or equal to Z. So the single instruction do the process of this statement. Thank you.